Hello, Ken. That's the whole class. It's two different people over here, two Kens. Hopefully there'll be more people. So I wasn't sure if people knew about this slot or not. I was going to look on seeing if we had announcements. There wasn't a calendar entry before. So what I'm going to do, the plan is that this slot, and we can see if we want to move it kind of to earlier in the beginning of the week. But the idea is for this slot, whenever it's going to be, that'll be some question and answers and another kind of mini lecture on some topic. And then that'll be recorded and people can see it. So even if people aren't coming, they'll get a lecture on whatever topic we're going through that week. I only put the post out kind of recently, so if people didn't know about it, that's fine. Gives me a chance to record some slides on a particular topic anyways. So if anyone does have a question, feel free to put it in the chat or unmute yourself. We're trying WebEx here, so I don't know if everyone has the ability to unmute themselves. If you don't, you can go into the group chat and I should be able to see it. As we're going, we're still trying different tools. This one has the potential, I like that WebEx is supposed to be able to save the videos directly to MP4. So I can put them up on the YouTube channel and then it'll all be in one place. So if you guys prefer the Rabongo recordings, the virtual classroom things versus this, you should let me know as well. So if there are any questions, like I said, I'm free to chat about it. As I said on the Wednesday live lecture section, we're in week 2. And if we go to the original kind of course outline here, that has altered, I guess, because you don't even care about my office number. So we're in week 2. But as I clarified in the Wednesday thing, I'm seeing weeks for this course to basically start on Wednesdays. So we're just kind of halfway through, not even halfway through week 2, because my other course is on Mondays. So that one starts Mondays, this one starts on Wednesdays to Tuesdays. So if it feels better to have some kind of live meeting like this on Tuesdays, which is a wrap up, and then Wednesday is the beginning, we can do that too. So the idea is we're kind of going through, we should be reading through contents, materials from the Sutton and Bartow book on multi-arm bandits and the Markov decision processes. These are kind of foundational concepts for the course. What we're doing with the Ginkgo tree list, which you should all have access to, right? It's got all these kind of resources we're going to add. Hopefully we're going to integrate that into a new live website as well, but we can just post the markdown straight there and it should work. So we're in week 2 and we're going to update these sections. So you should be reading through these sections of the textbook this week. And then as the lectures become available, we're going to add them in here, right? So the previous lectures on multi-arm bandits are up already there, so you can kind of see them. I'm going to continue on that and then get on to the basics of Markov decision processes. It's the essentials. So like I've said previously, the textbook has kind of more details, and then if we have other websites that are relevant, like we'll link to these today, you can read them as well. So the lectures are really just the high level picture or the most essential points that I think we need to make sure are covered. There's more stuff that you can have in there. And I guess I'll have to clarify before tests which parts are actually essentially could be on the test, but it'll be limited to at most what's in the textbook or the slides that I give you. So extra reading stuff is to help you understand it, but I wouldn't be using the thing off the website unless I explicitly make that clear. All right, so what was I going to do? I was going to go to my slides then. So this is where we ended on the second session of video lectures, if you have looked at them. And we're talking about multi-arm bandits. So this website, which is the Analytics Diva blog, it has we're linked that in the Ginkgo, and it has some kind of review of some of the same concepts we talked about so far. But it's focused specifically on multi-arm bandits, and it has code for it in Python, so you can play with multi-arm bandits and use their code for it. And they give you a few of these use cases that I was talking about, where you're kind of using it for advertising, where the decision is do I show them this ad or not? Do I send them this coupon or not? Basically, if I sent them the coupon, would I strike it rich by them actually using the coupon and buying something from my store, right? That's kind of the idea. And it's quite widely used, and it lets you kind of, there's other reasons you can go into an entire course about the probabilistic kind of reasons why it's kind of useful and lets you put in your own kind of priors and information. So we have notes on that, but that's not the direction we're going to focus on. What I want to see it for is to help us understand what decision making is and how we learn from evaluations, and then use that to kind of update our values, right? So they have the same kind of formulation we had of the value function Q. In this case, we're just saying it's still just the action. So we take this action, how much is it going to get us? So it's the expected long-term reward for taking that action. How much money you're going to make by standing in front of this machine and pulling it at the casino, right? Or sending that ad or whatever the choice is. So the reward you're getting each time from when you take the action, conditioned on the action you took, and this is that expectation operator. So we're combining the probability of each one happening by the reward, and that average essentially is what we're getting. So we've been looking at just maximizing that return, right? So how much money are you going to make, right? So another way to look at it, and this connects to casino as well, another concept is regret, right? You could say, okay, I'm not really evaluating how much money I could make. You know, is your success at the casino on the slot machines how much money you walked out of the casino with, or is it the sense of regret, like how much you didn't get that you could have got, right? Because if none of the machines were winning and nobody won any money, maybe you don't feel that bad. You spent 20 bucks on slot machines, you had some drinks, and it was fun. In the end, that you only lost 20 bucks, right? But if you walked away from a machine and then somebody walked up to it next, pulled it, and got $1 million, now you have huge regret, right? Because you could have won that money under the assumption that if you went there and pulled it, it would have won. Um, so that's kind of a useful concept conceptually, right? It's how much you possibly could have got. And you can actually measure that regret in terms of a bit more concretely, which isn't exactly the same as the casino one. But basically, what we're trying to say is how much reward we could have got. So if you eventually become perfect at at making your decisions, so you eventually master how much the arms get you, and you figure out which one gives you the most money and do it along the way while you're learning, right? If we had those examples last lecture where if we knew the distributions of the arms, we would know which one to pull, right? So if arm number 3 gives us the most money, we should just pull that all the time, right? But until we learn that, we're losing reward, right? If we just figured it out along so the faster you learn, the less regret you're going to have. So at least you're going to figure out which one's winning, right? And which one's the right choice. So you could measure what's the area above this curve, but less than maximum, right? Because you can't do better than getting the maximum reward you're going to get on average. And so we could use that regret to basically gauge how well we're doing. And this leads to a different kind of set of algorithms, right? So if you look at, from this point of view, if you look at one of those suboptimal things, so maybe it's the very perfectly greedy approach, it finds an arm that's pretty good, it tries all the arms and thinks that arm number 5 gives you the most money, even though it never really tried arm 3 enough to realize that. It gets stuck at some arm and stays there. So its regret's going to be infinite, right? Eventually, this will just keep adding, right? We don't want that. We want the regret to kind of converge down to 0. And so they have the same formulations we had, where we're saying here's the value. So it's kind of a repeat of the previous slides. You can look at this as an alternate kind of approach for understanding it. What else do they have here? This helps with understanding the probabilistic kind of view of the multi-arm bandits. They were saying if you want to draw out all the choices that you're taking. So imagine you have, with our epsilon greedy approach, right? Remember, an epsilon greedy algorithm policy is one where with probability epsilon, you choose a random action, regardless of what your value is. You know arm 3 is the best, but still with probability, say 1%, you're still going to pick some other arm just in case things have changed or in case you weren't right about your model. And with the rest of the time, you take your best action, right? So you could draw a tree of all the different scenarios here and what's the probability of you getting into this kind of region and taking that action. And then you could assess a value to each of these parts of the graph, right? So a slightly more complex way of doing this is to say that rather than saying the probability of picking a random action is greedy, you could have a softmax greedy. So this is kind of more complex than epsilon greedy, where you say we're going to take the values we have so far and basically determine that the probability of us choosing an action is based on the amount of value we expect to get from it. Right, so remember here, Q is a real number. It gets higher and higher the more value you've got from taking that action. So this is pulling arm 2 or pulling arm 5, how much money you got on average pulling that arm. And E is literally E, 2.7, whatever. So you're just creating a Boltzmann distribution or a Gibbs distribution. It has many names. But essentially you're putting an exponential kind of value of that, turning that constant into an exponential number and then normalizing it. So you get a probability here. It's definitely a Gibbs or Boltzmann distribution. If you remember from your thermophysics courses or whatever, if you have Boltzmann distributions, this is like your temperature term, right? And so the higher the temperature, or is it 1 over the temperature, then the higher the probability, right? So the lower the entropy. So the higher this value is, the more likely you are to choose it, right? So this means that now you're choosing an action based on most likelihood, but if something is not, as long as they're not all 0, you'll still have some chance of choosing a non-optimal thing, right? So this is kind of a more complex, greedy approach that explores your actions in proportion to how much you expect to get, right? And you could put penalties in here to make that basically encourage things that are very low. Delayed epsilon greedy, we talked about that. That's kind of having a weight on the so the next thing we want to get to though is this upper confidence band. So they have yeah, so they have some nice graphs here, but in the other one we have kind of definition. So upper confidence bound is really one of these core algorithms that is used a lot for multi-arm bandits, and it's the basis of many other kind of interesting advances in the last even just 10, 15 years. And so it goes another complexity level beyond what we've talked about even this way, saying how do you know when you've tried an action enough, right? And the idea is you build a bound, a probability bound over each action and how much you know about it. And you want to build one that is optimistic but correct. So you're not overestimating how good an action is. But as you learn more, it's going to kind of flatten. It's going to become less flat. So at the beginning, you'd never taken action before and has some kind of very distributed, spread out probability. So this blue one, QA1, is like if you've only 3 different arms, right? So arm 1, we've never hardly taken it at all and has a default very broad probability. And as we take more samples of an action, so arm 3, we've pulled a bunch of times, we know more about this, right? So we're pretty sure its value is somewhere in this range. And if it's the arms from the example that we used in class before, then it's literally like Gaussian, and there's a mean and a variance. And at some point, you won't be able to do better than this because you'll really have a model that predicts it, right? But the value of that doesn't have to be a Gaussian. Oops, there we go. Right, so that's just kind of one way to think about what we're doing. And I had a applet somewhere, I'll try to find it, where you can kind of do that, run it, and see them evolve, right? Because you imagine as you take each action, as you each pull each arm, these curves will kind of move and go up. And if you're doing greedy, right, you're always just taking the one with the highest peak, right? Where do you think is the highest probability? But that's just a way of seeing what we're doing here. So if we go to the slides, we have this definition of UCB all in one slide, and the textbook has a little bit more. So the function that we're optimizing here, rather than just optimizing Q, right? Because the default thing is we're optimizing Q. What am I going to do? Oh, that's not very good. I've changed tools, of course. I change tools every lecture. That's my rule. Always why I don't like those. Okay, that does work. By the default greedy one, we're just using maximizing the action, then maximize Q, right? So here we put a penalty that says, or a bonus, I guess, is to reduce the exploration by having an estimate on how good this could possibly be, right? So for an action we're going to add an additional estimate which says we're going to measure the uncertainty, right? So the square root and n, remember, is the number of times we've pulled that action. So how many times have we taken this particular action? And then we're going to scale it as 1 over the square root of this. And the log lets us basically scale it over time. So remember we had alpha, or we haven't talked about gamma yet. What alpha we had where as you go back further, you don't care as much about the distant rewards that you got long ago. That's going to happen with this log term. So the higher we go, right, this will become smaller. So this whole thing will become bigger, right? Because as this gets 1 or 0.1, this number is going to be higher. So this number is going to get bigger and bigger as we go. So we're going to like looking at the most recent actions, times we've counted that action. And we had an optimality thing before about the square root kind of giving us a better sense of the probability of that statistic. So that's why that helps. And then C kind of does what we had alpha doing before, but in a different way, where we're controlling the exploration. So if C is higher, then we're more confident in our values, right? Because we have the value for this action, and we're giving it essentially a bonus based on this estimate of how many times we've seen this action, and how many times we've gone forward in the model at all, right? So what this does, though, and they have kind of reasons that kind of show how it works, that you get a better estimate, right? So rather than having this epsilon greedy approach in the upper confidence bound, you're kind of having a proper probabilistic estimate of how good this action could be. And so it gives you a statistical kind of measure, right? So if we've had 1 million samples already and we've only seen it so many times, this is going to become less relevant. But at the beginning, it'll let us kind of get a better gauge. So the beginning, in this case, we're being more cautious, right? Because it's not doing as well. But once we get higher up, we kind of realize we've learned everything we have to learn about it. So let's see if the other slides of the paper had something here. So this one had a bit more description of right, that's why I wanted to show you, use this thing. So you can read through this and see a bit more about why this equation kind of helps with that. So as the number goes, so as the number of counts goes up, that term at the end goes down. So your uncertainty is being reduced because you know more about it. So there's no need to give it a bonus anymore, right? So if you don't know anything about it, then you want to give it a bonus. And that's what we did with the optimistic values. We say, well, let's set all of them to 5 initially and assume they're really good. That's a really dumb way to do it, but simple. And then once you learn more, they get less important. This one kind of has a measure the same. Well, how many times have you visited in proportion to how many steps you've actually taken, right? So you need to say that we've got a balanced level of understanding and probability about all the different actions we could take, because the number of steps, T, that you're going forward and the number of times you tried each action, NTA, are being traded off. And you basically, if you go for a very long time without sampling a particular action A, this will keep going up and you'll have more chance to sample it, right? And so that gets you to the optimal action much more quickly, and it's kind of proofs about how this converges better and everything. So UCB is the basis of a lot of kind of forward tree search approaches in reinforcement learning that let you kind of choose amongst your actions and aggressively exploit while exploring kind of the minimal you need to. And so when they plotted out with regret, so before we were showing the values with the rewards, so there are the rewards just going up and up. Here we're plotting the regret, right? So in this case, you want the regret to go down, right? You want to say that curve where the regret over not learning faster and losing out of money before you figured out the optimal machine is minimized. And so when you do experiments on that, UCB is very good at minimizing the regret, right? So it may not be good right at the beginning, right? Greedy or epsilon greedy might get you more reward right off the bat, right? Because here low regret is better, right? So epsilon greedy is doing the best, and greedy is going to be always worse in this particular case, whatever they tested it on. But UCB wins out in the long run because it makes sure to test all the kind of less rewarding actions until you really have a tight enough probability, and you essentially have tightened up all these curves so that you really know that action A is just less than A3, right? Because maybe this outlier for A1 explains some of the reward and you were just unlucky at the beginning, right? So this is more kind of properly bounded ways of doing that. So in this blog, just to kind of complete through that, they also have some issues about non-stationarity, and there were some questions on Piazza about that had some good answers, I think. So you can kind of look there. Right, non-stationary is when the rewards you're getting keep changing. So the game you're playing changes, right? Maybe the agent gets harder, or you go to a new board, or just the world isn't consistent, right? And if you're ever in a domain where the other agents you're playing against can learn, or where the world is open-ended and maybe you're interacting with different things over time that can change, then you got to assume it's non-stationary. So they have some code there you can run. Here you go, for trying out multi-arm bandits and UCB and some simple domains. Let's see if they had anything else about. No. So that's a useful website, though. What else do we have? Okay, so we go back to so that's the one we have here. So that was our comments bound. So then I have a few more slides on things that aren't necessarily super important, to just give you kind of other views. So the gradient part of this, I wouldn't worry about so much, but the important part, baseline is a neat idea, and that's something that'll come back in later when we get more to. So don't worry too much about this when we think about policy. Oh, right, that's why I don't use this tool. Policy gradient methods later. I'm writing with my mouse, so that's why it looks like I'm 3 years old. So policy gradient section, which is going to be weeks and weeks away, right? We're talking about week 6 or 7. That idea will come up again. But it's just to kind of say it here, because it does relate to understanding these rewards. Baseline is kind of like, assume you've got a kind of a good estimate of the reward at some point, and then what you do is measuring how much you've learned since then. So you have your average reward that you had from a previous time step, and then you're really trying to say, is this new action I'm taking increasing my reward or increasing my knowledge in some cases when they do it, or decreasing it. And so you use the difference between what you got this time and what you had expected to get over your average to figure out whether it was a good action or not. But this whole thing about H being a preference, taking the action, we're not going to use that initially. So it's just another way of making that choice. Right now we're taking, what's the maximum or some kind of maximum of the Q function. So this is just yet another trick that you can use that helps kind of improve above other things for sampling. But I think we'll come back to it when we get to direct policy search. With the bandits, another way to look at it is that we're basically fitting a, like I said, we're fitting a probability distribution, right? That we're trying to basically learn these counts of how many times we take an action and what reward we get for it. So you can think of it that we're trying to basically estimate the probability of getting a certain mean reward from some action. So you could write that down as a probability function where these theta are parameters that kind of define that probability distribution. So in a Gaussian, the thetas are the sigma and the mu, right? Those are the theta values because they're the parameters that tell you what the probability distribution is, right? So we assume that in our very simple model we talked about so far, and the count is your I guess probability, your parameter. So there's things that you can do to basically connect multiple distributions together. And I don't know if we really need that for this. I'll link, there are some other links to things on this that are very related. So you want to go off in that direction and find out more about it, especially related to A/B testing and advertising. They build these probabilistic models and connect them together. But I'll connect you guys some more notes about that because I want to talk about this algorithm and then show the MDP part. So because the reason this is just kind of motivation of another reason why we have to build a simple estimator, and this algorithm of Thompson sampling is kind of a very powerful and simple way of doing that. So it's an old method. It was used in the 30s for something, but no one kind of rediscovered it until recently. We are talking about artificial intelligence, not Al, some guy named Al. He discovered it 20 years ago. AI does that a lot. So they say, oh, here's some new idea. We discovered something that's fantastic. And then everybody realizes it's some mathematician in the 20s or economist in the 50s had that idea and was using it for some very theoretical thing. And then it wasn't until the 80s or 90s or 2000s that somebody thought of using it for computers or artificial intelligence, and then it becomes popular. So there's always a little bit of a like, oh, realizing it's actually old. Nothing's old. So we have our epsilon greedy algorithm that we've talked about already, right? And it's pretty good, and we have ways of making it slightly better by putting optimistic priors in. But it still does a lot of sampling, right? It says that you kind of randomly sample off your optimal approach to doing that. Rather than picking your optimal action, you randomly pick something, right? So upper confidence bound that we just talked about is one way of trying to do that more efficiently and targeting it by using this particular formulation. And Thompson sampling is kind of another way of doing that, where it's a way of implementing UCB as well. So it kind of self-corrects automatically because you take some samples and then you learn that you have enough information and you move on to something else. And people have been able to prove convergence results for it to show that it converges as long as you're sampling all the actions kind of infinitely often. And it helps you trade off this, because there's exploration and exploitation, but there's also exploration of really unlikely ones, like in your actual life, exploring playing the lottery to keep the gambling thing going and buying lottery tickets. Well, maybe Lotto 649 is better. Maybe if I play Lotto 649, I'll have more chance to win than playing Lotto Max, right? But no, your odds of winning on any of them are very low. You're probably much better off just keeping that money in your pocket and doing something else with it, right? Because they're all bad. So if you want to get enough of an estimate to say this is just very unlikely, you can stop exploring it, right? You want to explore things that are actually possible to win. And so they have some plots kind of describing why this is so inefficient, right? Because if you start off with some function, like the red one here, action 3, if that's its true probability, you don't want to spend a lot of time learning this curve, right? You say, well, it seems really bad. Someone's getting this, someone's getting that, and it's all over the place. But I don't get a high reward very often, whereas these guys always give high rewards. So at some point, you want to just give up on learning action 3, right? Even though exploration is important, you don't want to do it very much. And so the algorithm here from the slides related with the textbook um, is a simple way to look at it, but I have another link that's a bit better. So what are we talking about here? So it's still choosing an action according to the probability that maximizes the reward. So connect similar to the UCB thing we had, but it's kind of more general now. So we have some kind of probability function, right? Which is a probability of we're going to get a reward, and it's based on the action we're going to take, based on X is probably any other information we have. Yeah, that's why I don't use this. About the state or the situation we're in, and then bandits, that's going to be empty. And then theta are some parameters, right? So if it's the parameters of your Gaussian, they could be that. If it's the counts of how many times you take no action, it could be that. And then you've got this. So in our UCB, we've got a formula for this probability, which is square root 1 over n. And before we had, the sum of all the rewards divided by the counts. So this probability can be quite simple, or it could be a whole function, right? But then the thing about Thompson sampling is they use these kind of priors to say you have some idea of where these things start off, and then you do the Bayes rule kind of formulation. So we talked about that in some of the background descriptions, right, where you can turn around the probability. So rather than sampling, rather than is here data, or D is all the data that we have collected, and theta are just the parameters that we're trying to fit. Well, the data includes the rewards and the actions and anything else we've seen. And what we're trying to do is figure out what's the right parameters of this function given that data, right? Because we see these are the things we observe. This is the thing we assume that we're given. And we use this to say, well, what I want is to have an estimate of those parameters. So you iteratively kind of update the parameters of that model, and then you improve it. So if let me see if this makes sense from the stuff we've talked about so far. Where's what time is it? Okay. So here's our greedy, and so we're calling it Bernoulli greedy from this slide. I moved some of these around last year, and I'm trying to remember. It's still argmax, so trying to see, this notation is different than what we talked about in class. So we're estimating our model. So ignore think to yourself, what is theta in this case? We've got alpha, we've got k, we've got beta. We haven't defined any of these terms, so I'm doing it very badly. But this would be, because they're doing data Bernoulli, this would be wins versus losses, right? So that's the thing I didn't have. So if you, and especially if it's for the bandit, this is where you won money. And then these are ones where you lost money, pretty sure. All right, so we're counting together all of the, all of the pulls, all of the actions you've taken, and you're basically saying that my expected probability of winning on this arm, of making money, is just the ratio of how many times I've won versus how many times I've pulled it, right, on that arm, right? And so I guess in our scenario, this would have been NT of A, right? And this would be the others. Well, this total, the entire total would be that. That would be the entire under this fraction. And so we're still doing a max. So I guess in ours we have Q. So Q is the model that we're learning. And we're trying to decide what action to take. So we're still maximizing something given our model, but here it's being written as theta rather than Q. I'll go in and confirm this and give you guys the reference for this after. I'm not sure where I pulled it from now. It's and then we take that action and we see what reward we get. So the structure here is still the same. So we're basically just using counts and we're maximizing some model to take our action, and we observe it, and that's it. And then we update our distribution, and here you're just adding the reward, right? And you're subtracting the reward. So these are going to be the total amount of money you've won and the total amount of money you've lost, I guess, in terms of regret. So that is a little different. We're actually tracking the money you could have got. So I guess to see what the only difference is that here, instead of sampling this 1/n type thing, they're sampling a probability distribution that uses these. And so that's the part that I can link you to more other things on. It still uses accounts, but it does it with a probability kind of function, and you can have some priors on to say how likely it is that something would change with more observations. But then otherwise, the algorithm is exactly the same. So you still maximize that value, and you observe it, and then you update your counts. So we'll see that a lot in the different algorithms we're doing. They'll get a bit clearer once we have states in here. But where, there's this structure, which is build an estimate of your model somehow, maximize it and choose an action, interact with the world and find some rewards, and then update your model. This kind of pattern is going to happen in almost all the algorithms, but the way you implement each of these could be quite different, right? And the reason we start with bandits is that this structure is a bit more clear. And once we start saying, well, now it's not only that you have to choose the action, you also have to consider what state you're in, right? So when the action is, should the robot move left or right, it's also relevant. Is it out of battery power? Is there someone standing in front of it? All those things. Here, you're not worrying about that. You're worrying about which arm do I pull. It doesn't matter what day of the week it is or anything, and you don't know what's going on in the arm. So hopefully that kind of helps a bit. So they have some plots. I'll go back to that regret slide in a second, talking about showing them on some experiments where they've got greedy. There's various ranges of greedy, and then Thompson sampling. So Thompson sampling is kind of the optimal way to make these choices, right? And I guess, yeah, there is a comparison of UCB after. So Thompson sampling and UCB are kind of two similar ways to do this, but the way they build that estimate's a little different. And this kind of gives you this, it gets the regret down very quickly, right? So here we're talking about regret, and here we're talking about how far you're from optimal. So when we say distance from optimal, we're saying that this line is the perfect you could do. If you knew the best possible action, which arm gave you the most money, you just pull it all the time. And you will get there eventually, but the idea is that you want to reduce it as quickly as possible. So given the right model. So we have another formulation of regret here. So here you can see that we're modeling the reward as a well, we're not saying it's not necessarily a Gaussian. Some function of the action we're taking and those parameters, but it's just the, I need to give you guys more context for that, for what G is, because we didn't define that. So I'll go find where this slide came from and give you more content. But you can see there's a difference, right, in the regret. So we're kind of subtracting from kind of the optimal that we know of and what we saw. So we're really computing at every step how much we lost out on, and that's what we're measuring rather than the total reward. Right, so like I said, these two algorithms are kind of different ways to do that. We're trying to be optimistic about our actions, but do it in a way that's probabilistically, kind of statistically sound. And they maximize this Bayesian regret that we're referring to. And we're not going to go into too much, I guess, detail justifying the regret. If I'm going to ask for more on that on test, I would have to give you more content. But knowing that that's what they optimize, and how regret's different than reward, that's important. And they have interchangeable bounds. So they're not exactly the same, but they can be interchanged with each other. So they have a relationship, and it's not clear one's, I think, better than the other. They just have a different approach. But I remember at some point 10, 15 years ago, Thompson sampling was like, everyone was super excited. It was like, oh, it solves everything. It sounds like it was going to be the ultimate everything. But maybe for bandits, it really is one of the better ones. And tutorial section too. I don't remember having that slide. So we had some limitations with Thompson sampling. I'll have to find where those slides are. But from these definitions they plot out, I think on that 10-bandit problem that we had earlier, all these different algorithms on a bunch of sample runs. So you're running 1,000 steps, averaging the reward and trying some different ones. And what are we doing here? So here are, each of these algorithms has some parameter, right? So epsilon greedy, you've got a random chance of choosing suboptimal, right? And the averaged kind of discounted exponential time discounted reward thing, alpha, you're saying the past kind of drops off in importance. You only care about recent rewards. For UCB, we've got the C value, which kind of how much bonus you're giving, being optimistic about things. And Q0, I guess, is your initial reward for the first thing. I'm not sure how that scales in these algorithms, which one's using it. And so they're averaging this out and showing how there's a sweet spot for each algorithm in terms of these parameters. And depending which domain you use, the sweet spot would be different, but you would expect it to go up and go down, that you're trying to tune each of these parameters to figure out which one will work best. But there is a clear hierarchy, right? That these I guess they didn't put Thompson sampling on this one. This is from the textbook. They didn't have Thompson sampling, just UCB. But Thompson sampling would be similar to UCB, kind of a slightly different curve, but in the same ballpark. And so some type of optimistic thing with the proper weighting, or these UCB things are often much better than these greedy approaches. The problem with optimistic, so optimistic seems really good. The problem is you have to weight the optimism, right? In our example in that, we said, okay, QA equals 5, right, for all of them. So you have to come up with that and say, well, how optimistic? What's the right value? And you also still have to adjust this weight. Whereas UCB and Thompson don't have that. They automatically adapt. What you do have to say is, what's the distribution of values and how you're going to learn them? And so you still have to put some priors, but it's essentially a bit more like putting down your beliefs about how a fair coin works, and that as you learn more, the probability is going to get tighter. So it still has some parameters, but they're a bit different. This one's quite arbitrary. So that's this second part on I guess that's everything on bandits we had. It's a simple model of decision making with no states. We've introduced how values and actions interact and how we can learn from them. And there's a bunch of different tricks we can use kind of to initialize the estimates differently or to update our beliefs. And all of these tricks have different pros and cons. And that's going to be true even as we get to more complex domains. But what we really need next now is to say there's one part that's missing, which is the state of the system, and we need to add that in, and that's what the next topic is about, which I won't continue right now because our time will be up. I'll stop here for this recording, but the next topic for this week was to read about markup decision processes. So you have that section of Sutton and Bartow, those chapters listed here in the Ginkgo. We'll be talking, so MDPs are really core kind of concept for reinforcement learning. So that's the next thing to look at. And you can read about those. That's all I have for now, and I'll stop the recording for the lecture part. And if anybody does have any questions, we can have a couple minutes